what I want to do in this video is come up with a relationship between the area of a triangle and that triangle's circumscribed circle, or circumcircle. So before we even think about the circumcircle, let's just think about the area of the triangle. So let's say let's say that the triangle looks something like, let's say that it looks something like that. Actually, I don't want to make it look isosceles, so let me make it a little bit. Let's make it so it doesn't look like any particular type of triangle. And let's call this triangle capital A, capital B, capital C. That's the vertices, and then the lengths of the sides opposite capital A is lowercase a, lowercase b over here, and then lowercase c. Now we know how to calculate the area of this triangle if we know its height. So we can drop an altitude right here. We can drop an altitude right here. And if this altitude has length h, we know that the area of ABC, and writing ABC with the brackets around it means the area of triangle ABC, is equal to 1/2 times the base, which is lowercase b, times the height. Fair enough. So we have an expression for the area. Let's see if we can somehow relate some of these things, or the area, to the radius of this triangle's circumscribed circle. And so a circumscribed circle is a circle that passes through all of the vertices of the triangle. And every triangle has a circumscribed circle. So let me try to draw it. This is the hard part right over here. So it might look something like this. That's fair enough. That's close enough to a circle. I think you get the general idea. That is the circumcircle for this triangle, or this triangle's circumscribed circle. Let me label it. This is, that was a weird looking arrow. This is the circumcircle for this triangle. Now, let's think about the center of that circumcircle, sometimes referred to as the circumcenter. So it looks like it would be sitting, I don't know, just eyeballing it right on this little b here. So that is the circumcenter of the circle. And let's draw a diameter through that circumcenter. So let's draw a diameter from vertex B through that circumcenter. So then we go there, and then we just keep going over here. And let's call this point over here, let's call that point over there D. Now, let's create a triangle with vertices A, B, and D. So we can just draw another line right over here, and we have triangle ABD. Now, we proved in the geometry playlist, and it's not actually a crazy proof at all, that any triangle that's inscribed in a circle where one of the sides of the triangle is a diameter of the circle, then that is going to be a right triangle. And the angle that is going to be 90 degrees is the angle opposite the diameter. So this is the right angle right here. And you could derive that pretty straightforward. You have this arc here. You have an arc here that is 180 degrees. That is 180 degrees, because obviously this is a diameter. And it subtends this inscribed angle. And we've also proved that an inscribed angle that's subtended by an arc will be half of the arc length. This is a 180 degree arc, so this will be a 90 degree angle. So either way, this is going to be 90 degrees over there. Now, the other thing that we see is we have this arc right over here that I'm drawing in magenta, the arc that goes from A to B. Well, that arc subtends two different angles in our drawing. It subtends this angle right over here, angle ACB. It subtends that right over there. But it also subtends angle ADB. That's why we constructed it this way. So it also subtends this. So these two angles are going to be congruent. They're both going to have half the degree measure of this arc over here, because they're both inscribed angles subtended by the same exact arc. Now, something interesting is popping up. We have two triangles here. We have triangle ABD and triangle B, I don't know, we could call this E, and triangle BEC. They have two angles that are the same. They have a right angle, and they have this magenta angle, right angle and this magenta angle. So their third angle must be the same. I'll do that in yellow. Their third angle, this angle, must be congruent to that angle. So they have three angles that are the same. They must be similar triangles, or the ratio between corresponding sides must be the same. So we can use that information now to relate the length of this side, which is really diameter, it's 2 times the radius, to the height of this smaller triangle. And we know a relationship between the height of the smaller triangle and the area, and we are essentially in the home stretch. So let's do that. So these are two similar triangles. So we know that the ratio of C, we know that the ratio of C to this diameter right over here. But what's the length of the diameter? The length of the diameter is 2 times the radius. This is a radius, and this is a radius right here. We know that the ratio of C to 2 times the radius is going to be the same exact thing as the ratio of H, and we want to make sure we're using the same side, to the hypotenuse of that triangle, to the ratio of H to A. And the way we figured that out, we looked at corresponding sides. C and the hypotenuse are both the sides adjacent to this angle right over here. So we have H and A over here. So C is to 2R as H is to A. Or we could solve, well, we could do a lot of things. So we could just substitute, we can solve for H over here, and then substitute an expression that has the area in for H. Actually, let's just do that. So let's say, so if we use this first expression that we have for the area, we could multiply both sides by 2. We can multiply both sides by 2 and divide both sides by b. And divide both sides by b. That cancels with that. That cancels with that. We get that H is equal to 2 times the area over b. So we can rewrite this little relationship as C over 2R is equal to H, which is 2 times the area of our triangle, 2 times the area of our triangle over b, and then all of that is going to be over a. Or we could rewrite this second part right over here as 2 times the area over, we're dividing by b and then dividing by a. That's just the same thing as dividing by AB. And so we can ignore this right here. So we have C over 2R is equal to 2 times the area over AB. And now we can cross multiply. We can have AB times C. I'll do a new color just to ease the monotony. AB times C. AB times C. AB times C is going to be equal to 2R times 2ABC. So that's going to be 4R times the area of our triangle. I just cross multiplied. This times this is going to be equal to that times that. And we know that all cross multiplication is just multiplying both sides of the equation by 2R and multiplying both sides of the equation by AB. So we did that on the left-hand side. We also have to do it on the right-hand side. 2R and AB. Obviously, that cancels with that. That cancels with that. So you get ABC is equal to 2R times 2ABC, or 4R times the area of our triangle. And now we're at the home stretch. We divide both sides of this. You divide both sides of this by 4 times the area. 4 times the area. And we're done. This cancels with that. That cancels with that. And we have our relationship. The radius of, or we could call it the circumradius. The radius of this triangle circumscribed circle is equal to the product of the sides of the triangle divided by 4 times the area of the triangle. That's a pretty neat result.